In this second tutorial video on Octave, I'd like to start to tell you how to move data around in Octave. So if you have data for a machine learning problem, how do you load that data into Octave? How do you put it into matrix? How do you manipulate these matrices? How do you save the results? How do you move data around and operate with data? Here's my Octave window as before, picking up from where we left off in the last video. If I type A, that's the matrix that we generated, right, with this command equals 1, 2, 3, 4, 5, 6, and this is a 3 by 2 matrix. The size command in Octave lets you, tells you what is the size of a matrix. So size A returns 3, 2. It turns out that the size command itself is actually returning a 1 by 2 matrix. So you can actually set SZ equals size of A, and SZ is now a 1 by 2 matrix where the first element of this is 3 and the second element of this is 2. So you can type size of SZ. This SZ is a 1 by 2 matrix whose two elements contain the dimensions of the matrix A. You can also type size A1 to give you back the first dimension of A, the size of the first dimension of A, so that's the number of rows, and size A2 to give you back 2, which is the number of columns in the matrix A. If you have a vector V, so let's say V equals 1, 2, 3, 4, and you type length V, what this does is it gives you the size of the longest dimension. So you can also type length A, and because A is a 3 by 2 matrix, the longer dimension is of size 3, so this should print out 3. But usually we apply length only to a vector, so length 1, 2, 3, 4, 5, rather than apply length to matrices, because that's a little more confusing. Now, let's look at how to load data and find data on a file system. When we start up Octave, we're often in a path that is the location of where the Octave program is. So the pwd command shows the current directory or the current path that Octave is in. So right now we're in this maybe somewhat obscure directory. The cd command stands for change directory, so I can go to c:/user/ang/desktop, and now I'm in my desktop. And if I type ls, ls comes from a Unix or a Linux command, but ls will list the directories on my desktop. And so these are the files that are on my desktop right now. In fact, on my desktop are two files, features X and price Y, that maybe come from a machine learning problem I want to solve. So here's my desktop. Here's features X, and features X is this window, is this file with two columns of data. This is actually my housing prices data. So I think I have 47 rows in this data set, and so the first house had size 2104 square feet, has 3 bedrooms. Second house has 1600 square feet, has 3 bedrooms, and so on. And price Y is this file that has the prices of the data in my training set. So features X and price Y are just text files with my data. How do I load this data into Octave? Well, let's type the command load features x.dat, and if I do that, I load the features X, and I can load price y.dat. And by the way, there are multiple ways to do this. This command, if you put features x.dat in strings and load it like so, this is a oops, typo there. This is a equivalent command. So you can, but this way I'm just putting the file name of the string in a string, and in Octave you use single quotes to represent strings, like so. So that's a string, and I can load the file whose name is given by that string. Now, the who command now shows me what variables I have in my Octave workspace. So who shows me what are the variables that Octave has in memory currently. Features X and price Y are among them, as well as the variables that we created earlier in the session. So I can type features X to display features X, and there's my data. And I can type size features X, and that's my 47 by 2 matrix. And similarly, size price Y, that gives me my 47 by 1 vector. This is a 47 dimensional vector, this tall column vector that has all the prices Y in my training set. Now, the who function shows you what are the variables that in the current workspace. There's also the who s variable that gives you the detail view. And so this also, with an s at the end, this also lists my variables, except that it now lists the sizes as well. So A is a 3 by 2 matrix, and features X is a 47 by 2 matrix, price Y is a 47 by 1 matrix, meaning this is just a vector. And it shows how many bytes of memory is taking up, as well as what type of data this is. Double means double precision floating point, so that just means these are real values, so floating point numbers. Now, if you want to get rid of a variable, you can use the clear command. So clear features X and type whos again. You notice that the features X variable has now disappeared. And how do we save data? Let's see. Let's take the variable v and set it to price y 1:10. This sets v to be the first 10 elements of the vector y. So let's type who or whose. Whereas y was a 47 by 1 vector, v is now 10 by 1 because v equals price y 1:10. This sets it to just the first 10 elements of y. Let's say I want to save this to disk. The command save hello.mat v. This will save the variable v into a file called hello.mat. So let's do that. And now a file has appeared on my desktop called hello.mat. I happen to have MATLAB installed in this Windows, which is why this icon looks like this, because Windows has recognized this as a MATLAB file. But don't worry about it if this file looks like it has a different icon on your machine. And let's say I clear all my variables. So if you type clear without anything, then this actually deletes all the variables in your workspace. So if I type whos, there's now nothing left in my workspace. And if I load hello.mat, I can now load back my variable v, which is my the data that I previously saved into the hello.mat file. So hello.mat, what we did just now, the save hello.mat to v, this saves the data in a binary format, in a somewhat more compressed binary format, so that the v is a lot of data. This will be somewhat more compressed and will take up less disk space. If you want to save your data in a human readable format, then you type save hello.text, the variable v, and then dash ASCII. So this will save it as a text or as ASCII formatted text. And now, once I've done that, I have this file, hello.text, has just appeared on my desktop. And if I open this up, you see that this is a text file with my data saved away. So that's how you load and save data. Now let's talk a bit about how to manipulate data. Let's set A equals to that matrix again. So it's my 3 by 2 matrix. Let's talk about indexing. So if I type A 3, 2, this indexes into the 3, 2 element of the matrix A. So this is normally we would write this as A subscript 3, 2, or A subscript 3, 2. And so that's the element in the third row and second column of A, which is the element 6. I can also type A2, colon to fetch everything in the second row. So the colon means every element along that row or column. So A of 2, colon is this second row of A. Right? And similarly, if I do A colon, 2, then this means get everything in the second column of A. So this gives me 2, 4, 6. Right? This means of A, everything, second column. So this is my second column of A, which is 2, 4, 6. Now, you can also use somewhat more sophisticated indexing operations. So I'll just quickly show you an example. You do this maybe less often, but let me do A1, 3, comma, colon. This means get all the elements of A, whose first index is 1 or 3. This means get everything from the first and third rows of A, and from all columns. So this was the matrix A, and so A, 1, 3, comma, colon means get everything from the first row and from the second row, and from the third row. And colon means, I want both the first and the second columns. And so this gives me this 1, 2, 5, 6. Although you use these sorts of more sophisticated indexing operations maybe somewhat less often. To show you what else we can do, here's the A matrix, and this was A colon comma 2 gave me the second column. You can also use this to do assignments. So I can take the second column of A and assign that to 10, 11, 12. And if I do that, I'm now taking the second column of A and I'm assigning this column vector 10, 11, 12 to it. So now A is this matrix that's 1, 3, 5, and the second column has been replaced by 10, 11, 12. And here's another operation. Let's set A to be equal to A comma 100, 101, 102, like so. And what this will do is append another column vector to the right. So now, oops, I think I made a mistake. Should have put semicolons there. And now A is equal to this. Okay, I hope that makes sense. So this 100, 101, 102, this is a column vector. And what we did was we take A and set it to the original definition, and then we put that column vector to the right. And so we ended up taking the matrix A, which was these 6 elements on the left. So we took the matrix A and we appended another column vector to the right, which is now why now A is a 3 by 3 matrix that looks like that. And finally, one neat trick that I sometimes use if you do A and then just a colon like so. This is a somewhat special case syntax. What this means is that put all elements of A into a single column vector, and this gives me a 9 by 1 vector that just has all the elements of A concatenated together. Just a couple more examples. I can also, let's say I set A to be equal to 1, 2, 3, 4, 5, 6 again. And let's say I set B to be equal to 11, 12, 13, 14, 15, 16. I can create a new matrix C as AB. And this just means, so here's my matrix A, here's my matrix B, and if I set C to be equal to AB, what I'm doing is I'm taking these two matrices and just concatenating them onto each other. So the matrix A on the left, and I have the matrix B on the right, and that's how I form this, this matrix C by putting them together. I can also do C equals a semicolon B. The semicolon notation means that go put the next thing at the bottom. So I would do C equals A semicolons B. It also puts the matrices A and B together, except that it now puts them on top of each other. So now I have A on top and B at the bottom, and C here is now a 6 by 2 matrix. So just say again, the semicolon thing usually means go to the next line. So C is comprised by A, and then go to the bottom of that, and then put B at the bottom. And by the way, this AB is the same as A comma B, and so either of these gives you the same result. So with that, hopefully you now know how to construct matrices, and hopefully this starts to show you some of the commands that you can use to quickly put together matrices and take matrices and slam them together to form bigger matrices. And with just a few lines of code, Octave is very convenient in terms of how quickly we can assemble complex matrices and move data around. So that's it for moving data around. In the next video, we'll start to talk about how to actually do complex computations on our data. So hopefully that gives you a sense of how with just a few commands you can very quickly move data around in Octave. You can load and save vectors and matrices, or load and save data, put together matrices to create bigger matrices, index into or select specific elements out of the matrices. I know I went through a lot of commands, but so I think the best thing for you to do is afterward to look at the transcript of the things I was typing. Look at the course website and download the transcript of the session from there, and look through the transcript and type some of those commands into Octave yourself, so that you can start to play with these commands and get it to work. And obviously, there's no point at all to trying to memorize all these commands. It's just, but what you should do is hopefully from this video you have gotten a sense of the sorts of things you could do, so that when later on when you're trying to program a learning algorithm just yourself, if you are trying to find a specific command that maybe you think Octave can do because you think you might have seen it here, you should refer to the transcript of the session and look through that in order to find the commands you want to use. So that's it for moving data around, and in the next video what I'd like to do is start to tell you how to actually do complex computations on our data, and how to compute on our data and actually start to implement learning algorithms.